Thanks, Brianna. Okay. So, first of all, my apologizes for not being able to present in person due to my workload, university teaching workload at Queensland University of Technology. My apologizes for that. Okay. So, this presentation is about how we can use thin steel sheets effectively to enhance the bushfire resistance of buildings. So, if you look at thin steel sheets, we have two systems. One is the shutters, and the other main component is the external walls. Okay, so this presentation is a kind of summary of three large projects where we are looking at how do we develop a bushfire resistant shutter systems, assess the bushfire resilience of buildings using computational heat transfer models, and then the investigation of localized failures of thin steel battens due to the pull-out failure of the roof sheet and battens at extreme temperature environment. Okay, so before I move forward on this topic, I wanted to showcase that the facilities and the research that we do at Queensland University of Technology here in Brisbane. So we have our own radiant panel, which is 2.1 meter high and 1.5 meter long. And we also have the 3 meter gas furnace, which is capable of simulating the standard fire curve, which is useful for the bushfire flame zone exposure testing for the AS 1538.2. And then we also have some limited access to the Queensland Fire and Emergency Services at White Island for some flame exposure test. So if you see in the middle photo here, one of the middle photo here, where we have tested this wall panel at their facility. Further, we are civil structural engineers. So that means we will do a lot of structural testing, and we also do obtain the structural capacity of members, mostly on steel columns, steel tubes, channel sections, wall panels, floor systems, light gauge steel frame wall systems. And then we also do some material property level experiments to understand the material behavior, especially at the powder sample level. So we have equipments to measure the thermal properties, say like thermal conductivity, the specific heat, the mass loss or the density. Say if you expose a gypsum plasterboard to a very high temperatures, how it behaves. So what is the thermal conductivity at 300 degrees Celsius? Because that is different to the thermal conductivity values at 20 degrees or 30 degrees, because it has already cracked, delaminated, or partially spalling happened. So we do have those equipments, and we do look at the material properties at different temperatures. In addition to this experimental setup and experimental facilities, we do a lot of computational modeling for structural capacity as well as for heat transfer. If you look at this on my right-hand side, so that's a wall panel. It's a wall panel made up of steel stud in the middle, and on both sides, the gypsum plasterboard. So we expose that to a fire and see how the temperature penetrate or transfer from one end to the other end. And we also work out the capacity of the stud at different temperatures, because the steel has its own mechanical properties, the yield strength and the elastic modulus or the stiffness at various values at various temperatures. So we do those dog bone, the tensile coupon test to obtain that, and we do the modeling to obtain those capacities. So that's our background. So we are known at QT or outside world as QT Fire and Engineering Lab. We do experimental fire testing, structural capacity, and then computational modeling for finite element modeling for structural capacity and for heat transfer analysis. And recently, we also developed a methodology using the advanced technologies. How do you do a heat transfer analysis for an entire building, for a large building? So this is one of the study, a pilot study that we did for our QT-owned building. That's a barracks. And we published a journal article. How do you map the local surrounding of that building, and how do you perform a fire scenario and see the vulnerable areas of the building. So we do have a research paper on this, and we are still working on this project to understand the behavior of the building using its architectural features as well as the materials. Right. So that's our background. And then I'll move on to this topic. So this presentation is mostly about the steel cladding or steel shutter systems, and then the capacity of the battens, steel battens. Right. So now when you look at the temporary sheltering option for the disabled or unable, the people who can't evacuate, then most of the buildings will fall into category 9A, 9B, 9C. That means they have to be designed to withstand the bushfire. So that means we need the most vulnerable area for bushfire is the external envelope of the building. So that means that includes the shutter, that includes the external cladding material used for the wall and for the roof, plus the other material and other sections of the building like veranda and everything. So this presentation mostly focused on the first part of it, mostly focused on shutters, right? Before I go to the shutter section, okay, now how the thin steel section behave, okay? So one of the good material that we could use for bushfire protection is thin steel sheets. What I'm talking about is like 1.2 millimeter cold formed steel sheets. Because of course we know that steel will not burn, it will not spread fire, and it will not make the fire intense. And it has a very high melting point, about 1500 degrees Celsius. And it also resists the flame penetration and stop or delay the radiant heat transfer and protect the building inside components from embers. Say if a glass cracks, the embers can go over, but the steel sheet won't crack. So it will stay there and it will protect the glass panels from steel sheet, from embers. And then if you look at the other materials, say like timber could char or timber could ignite. Even steel could buckle depending on the load or the stress that it was subjected to. But if you use a thin steel sheet just for a heat transfer protection, it will not deform, it will not buckle, because unless if you have any overlapping issues. So if you protect that with the overlapping issues, and the splice, if you use it properly, the lap joints, it will not, it will safeguard the building. And also concrete, it could spoil or it could crack, or similarly the masonry materials also, it could do that. Right. Now, when you look at the AS3959, okay, it clearly says that all the components of the window assembly should be protected. Similarly, they have given the other guidelines, like any gap should not be more than 2 millimeters, and then some specific guidelines for BAL 40 and BAL flame Z conditions. Right. Now, when you look at the windows, the glass panels can be any type. It can be annealed glass, or it can be a laminated glass, or it could be a toughened or a tempered glass, fire-resistant glass, and ceramic glass. All these glass types has their own properties, own material behavior, at what temperatures they crack. Okay. Now, when you look at some post-fire investigation, the first photo on the right-hand side shows, okay, the annealed glass. This is an annealed glass that got cracked. And then this is another laminated glass, it got cracked. Of course, they are exposed to different temperatures. So how do you protect them? Okay. So when you look at the material properties of the glass, of course, it varies with the temperature. At different temperatures, it has different values. The density is constant, but the specific heat has different values. Specific heat means how much it will absorb. And then thermal conductivity means how much it will transfer or allowed to transfer through that. And then when you look at the steel sheet, okay, it has its own values. The thermal conductivity is very high here. Of course, for steel sheet, it will conduct easily. But if you keep it at a distance between the glass and the steel sheet, then it will protect your glass from heating up. And then some other materials are also given here, okay, for your reference. So steel will not melt. The steel will delay the temperature rise, and it will protect the glass from embers or cracking. Right. And then when you look at the literature, there were two basic studies. One is from the CSIRO, the other one is from CSIRO and the NASH. So they have conducted some window testing, the first one, and they have obtained the annealed and laminated glass will crack roughly around 200 or less than 200 degrees Celsius when it's exposed to, and the toughened glass, which is greater than 5 millimeter, will crack around 400 to 450 degrees Celsius. But bushfire temperatures, especially the flame exposure temperatures, are more than 500 degrees Celsius. And then the NASH and CSIRO conducted a house test with shuttered and unshuttered window for a 1 hour fire rated on the flame exposure side, and they both of them failed. The shutter one was, the shutter consisted of a roller steel mesh curtain with a 6 millimeter toughened glass. Right. So now what we are going to do is, okay, we are going to come up with our fire curves. Of course, the flame zone, we have the AS 1538.2, that is the standard fire 30 minutes fire curve. But we do have an alternative fire curve in the NASH handbook, National Association for Steel Housing, and they have worked out with the CSIRO to have a 47 minutes duration fire, which is more realistic of a pre-immersion phase, and then a flame zone exposure where the heat flux will be more than about 140, 160 kilowatts per square meters, and then a sudden decay phase, and then to incorporate the post-fire front radiant heat. And then what we did was, okay, for flame zone, we have that curve. Now for Bell 40 test, where you have only the radiant heat exposure, what we did was, okay, we used the AS 1538.1 curve, so that is 11 minutes curve, and then we modified the NASH curve to have a 47 minutes duration, but without the flame zone here. So without the flame zone exposure there, we modified it and we made it to 40. So now what we did was, to understand the material and the component behavior of the shutter and the window together, we have two different Bell 40 curves. One is a very short, rapid fire curve, that is the Bell 40 curve, which ends in 11 minutes. And the other one is a very prolonged 47 minutes duration fire, but without a flame zone. And then for the flame zone exposure, we have the exact curve in the NASH bushfire standards. Right? Right. Now, what are the configurations or the testing arrangement that we had? Okay. So for test 1 and 2, so that is the first Bell 40 exposure curve, we used 11 minutes and a 47 minutes. Two fire curves were there for Bell 40 without that flame zone exposure. We just had a 1.2 millimeter thick steel sheet in front of the glass panel. The glass panel was a toughened glass. Okay, so we just had a 1.2 millimeter at a distance of 130 millimeters, which is worked out based on the normal brick wall configuration. So we have a distance between the glass panel and the steel sheet, that is the shutter. So you can see it here, the bottom left corner, that's the glass panel, and that's the shutter. Okay. And then for the test 3 and 4, that's again for two exposures, but we had a mesh, a 1.64 millimeter aperture size mesh of stainless steel, a woven mesh. And then test 5 and 6 are for Bell flame zone exposures, so where we had a composite panel. So composite panel means test 5 had a 15 millimeter composite panel, so that in that 15 millimeter you have on either side you have a steel sheet, so that is 1.2 millimeter steel sheet, and then in the middle of the panel we have a 13 millimeter fire rated gypsum plaster board. And for the test 6, we had a 12.5 millimeter thick rock wool between those, sandwiched between those two panels. So that's the configurations. So in all of these cases, we have the steel sheet and then the steel mesh in test 3 and 4 to expose to the Bell 40 and then Bell flame zone conditions. Right. Now, a quick summary. So what we did, test 1 and 2. So test 1 and 2 is a 1.2 millimeter steel sheet. When we expose it to 11 minutes and 47 minutes temperatures, the steel cladding temperatures were 305 degrees and 325 degrees in both tests. And then the glass was only had measured about 64 degrees Celsius and 94 degrees Celsius for the BAL 40 conditions. Similarly, the mesh test 3 and 4, where we had 11 and 47 minutes. So that means that's the stainless steel mesh, and the glass temperatures were 126 degrees Celsius and 195 degrees Celsius, which means the toughened glass will survive. So just a steel mesh, 1.2 millimeter, 1.64 aperture steel mesh, and then the previous one, 1.2 millimeter steel, thin steel sheet will survive the BAL 40 conditions. Okay? So this was tested, and then the other two tests, which were exposed to the flame zone exposure based on the Nash fire curve. So if you look at that, so where you have a 13 millimeter fire resistant plasterboard, the glass temperature was only 87 degrees Celsius. But on the steel sheet, on the exposed side of the steel sheet, the temperatures were nearly around 800 degrees Celsius. So that was 790 degrees Celsius, where the flame came and touched the steel sheet or the composite panel. So this also will survive definitely. And then when you had the two steels and the rock wool, the last test, again, the fireside temperatures were 790 and the glass temperatures were 150 degrees Celsius. So that itself shows that a composite panel will survive the bushfire flame zone exposure. Of course, there are the fittings arrangements and the connection arrangements has to be worked out. It's a simple system, but it will for sure will satisfy. So now what we are doing is, of course, we are looking at different materials as well. We are testing some fabrics, some good fabrics which are performing well, but I just want to highlight here the steel sheet in this presentation. Maybe later on we'll include those fabric test results where you can hide those shutters under the ceilings and then roll it down. That's it, and then fix it. So now what we are doing is to better understand and work out the relationship between the steel sheet and the glass panels for various thicknesses, various distances between the glass panel and the shutters. We are trying to model that and do a heat transfer analysis. Okay, so we are using the fire dynamic simulator and we are measuring all the temperatures, and we have nearly come to a good agreement with our experimental results and we have developed the model. So that is where we are heading in the direction of bushfire shutters. And definitely we will do a large-scale test for the standard fire curve, which is the AS1538.2 for the 30 minutes rating. As far as we understood, if you could satisfy the Nash curve, it will become satisfied for the flame zone exposure for the AS1538.2. But of course, we have to test and we have to prove that. Right. Now the next section or the second part of this project is, okay, how do we have the steel cladding on the building and then the building can survive? So for that, we have come up with 4 different steel configured wall panels. So where in all the cases, we have the steel cladding on the external surface. And then if you look at the test panel 1, where we had the steel sheet, so as a 0.42 BMT steel cladding, and then a batten and directly connected to the steel stud. So this is like a very conservative approach. This is not currently used in practice, we understand that, but we, as a control panel, we developed this one. And then the next one where you have the sarking, and the third panel where you have the cavity insulation of glass fiber, and the fourth panel where we had a 16 millimeter fire rated board on the other side. And in all the cases, the internal surface was a 10 millimeter non-fire rated board. Okay, so the first 3 were exposed to the BAL 40 curves, where we have the 11 minutes and the 47 minutes test without that flame zone exposure or the flame immersion. And then the last one, the test panel 4, was exposed to a flame zone exposure with that 110 second very high heat flux value of 140 to 160 kilowatts per square meters. Right. So this shows the test setup and the thermocouples that we had on the panel. We nearly had about 35 to 40 thermocouples covering along the wall and across the wall, where you could see we have measured even on the flanges of the stud. Normally, when you go for a fire assessment testing a commercial well environment, they will not do all these things, but we do measure all these things because we just want to validate our computer model so that we can reduce number of tests and we can rely on the computer model's accuracy to do other configuration and understand the behavior, right? Right. So again, the same setup. So that's the radiant panel that we have. And you could see the wall panel. The wall panel that we used, because this is only for the heat transfer analysis, we only used 1.5 millimeter wall height and 1.2 millimeter wide. So that's only a heat transfer. So there is no load carrying capacity. And this is our QT-owned radiant panel. And the other one, the flame exposure, by left side test, we did it at Queensland Fire and Emergency Services. Right. And then, okay, because of the time restraints, so I'll only show the results of test one. So test one is a, test one is a simple wall panel, sorry. Sorry, okay. Right, okay. So previous, sorry. Right, okay. Right, okay. So that's the 11-minute test. So where the steel temperature, the hot flange temperature, somewhere here, it measured only 71 degrees Celsius, and the steel cladding was exposed to 337. So on the steel cladding, we had about 330 degrees Celsius for the BAL 40 conditions. And then the steel, the stud, because this is very important. The steel temperature of the stud is very important because that will prevent it from buckling. Okay, so that was only exposed to 71 degrees Celsius. And then the next one, the 47 minutes BAL 40 conditions again, the steel stud temperature, was only about 89 degrees and the cladding was only 300 degrees Celsius, right? And then when you look at the flame zone exposure test, where we had the 47 minutes and the flame came and hit the specimen, test specimen, we had the cladding temperatures 740 odd temperatures and the heat flux was about 163. So that is much higher than the normal BAL 40 curve. So that's 40. This is 160 kilowatts per square meters. And the steel temperatures were around 500 degrees Celsius, right? Right. And then, sorry. Right. Okay. So when you look at that 500 degrees Celsius, how do we transfer that to a load carrying capacity? Okay. So when you transfer that to a load carrying capacity, okay, right. When you transfer that to a load carrying capacity, it will come to a load ratio of roughly 0.4 to 0.6. Now, what is the load means? Okay, how much the steel can carry at an elevated temperature than the ambient temperature. Okay, so when you look at that, okay, of course, when you design, you normally end up with 0.4 to 0.6 load ratios. So when you design for a building for ambient at room temperature to the fire, you will end up with a 0.4 to 0.6. So that's lies for the steel cladding wall panel as well. So, but how? So that means we can still use that steel cladding to protect the building from the steel stud from buckling. Right. The overall summary of the wall panel is, of course, no visible damage was observed during the radiant test heating, but however, the flame immersion testing had some discoloration and some cladding layer deterioration. Of course, after the test for flame exposure, it had some deterioration. The sarking melted away, flame zone conditions, even prior to the flame zone was exposed. Okay, so now we have the temperature profiles. Now we have the measured temperature profiles so that now we can model them in the computer heat transfer analysis and obtain the and make our model validated, and then we can look at different configurations within our limit. So we are heavily using the fire dynamic simulator software, where you can see the layers of the gypsum plasterboard, batten, and the steel stud, and then the gypsum plasterboard layers, as well as we are working on finite element modeling analysis to obtain the steel capacity at higher temperatures. Okay, so that's what we are doing as a next step. Right now, the third section is okay. Now, during a bushfire, of course, all the roof material is exposed to a very high temperatures. It could be 200, 300 or 400 degrees. So that means our steel battens running below the steel section also could be exposed to very high temperatures. So if you look at the AS3959, it doesn't say anything about the pull-out capacities, but it clearly says some guidelines for designing the roof. Okay, right. Now what will happen? If you have a strong wind on the windward wall, you will have suction on the roof and suction on the leeward side of the house. So that means the roof batten, the roof sheet, and then batten, and then rafters. So that means this could pull out because of the suction pressure. This will easily pull out. So we have seen some post-fire failures of shed and other places where the batten, the sheeting has pulled out from this screw. Okay, so what we did was, okay, we tried to do it and obtain the ambient at room temperature capacity for these battens. So we did some small scale testing to see what is the capacity at room temperature. So we did some screw fastener pull-offs from the batten surface, and the tension action on the screw fasteners create pull-off failures. And then we came up some test setup to look at very high temperatures. Okay, so what we did was, okay, this is our electric furnace. We made a small sample and we pulled that screw, okay, at different temperatures. You could see here from 20 degrees at a steady state, 200 degrees, 300, 400, 500, 600 degrees. And we repeated those tests every time for different screws and for different steel gauges, 300 low strength and then the high strength. Okay, a number of tests were repeated to obtain that capacity. And you could see the failure photos and then the graph, the load versus displacement curves at different temperatures. So if you look at 300, 400, 500 degrees, so what will happen? If your batten is heated up to 300 degrees Celsius, there will be a reduction of 3% in its load carry capacity than the ambient temperature. But similarly, when you look at, if your batten is exposed to 600 degrees Celsius, there will be 81% reduction in the capacity, 81 reduction. And then 500 degree means that 53% is decreased. The capacity is decreased. So all these values we have incorporated into the room temperature capacity equation, and we have come up with a design rule to obtain the capacity at different temperatures for the pull-out failures. Okay, so this equation can be used now. If someone says, okay, my roof is going exposed to this temperature, and they know the batten temperatures, at what temperature it can go up for the bell 40 or bell flame zone, then we can substitute these numbers and get the capacity based on those pin pressure coefficients. Right. So these are some of our recent journal articles looking at various aspects of the bushfire resistant design, external walls, and then using the advanced technologies and developing some new materials, adding some new lightweight materials and naturally available materials into the normal beser block to enhance its usage for different applications. One application could be a bushfire safe room, because we are going in that direction. So we need a very highly fire resistant materials. So one way of doing is adding some materials and aggregates into the normal beser block and make it very enhanced. All these details you can obtain from the QT Wind and Fire Lab research papers. And then one of the last slide, which I want to highlight to you all. Of course, there are two sections. One is fire prevention. The other one is fire protection. And we are working on structural engineers, civil structural engineers. We want every building to be protected, designed and protected, so that we are trying to work out its capacities. Thank you.
Thanks so much, Anthony. Now, do we have any time for questions? I'm not sure. We do have one question from the floor. Do we have a microphone? Just hang on a sec. We've got a question for you. And if you do have any further questions as well for Anthony, please enter them into the app, and hopefully, if you've got time, you can get to them later. So here's your question.
Hi, Anthony. Rod
Yeah.
Olone here. I got really excited when I saw an R-squared value of 0.98, so I'm really excited about that data, so fantastic. My question is related
Yeah.
to the test 3 and 4 that you showed us earlier on
Yeah.
with the woven stainless steel mesh. Why did you choose a stainless steel and not a mild steel?
Yeah, we did do for mild steel. The only reason we just chose the stainless steel is, okay, of course, that will be a good one for corrosion to prevent for a durability concern. And that is the only reason that we chose stainless steel, but we do have results for mild steel as well.
Okay. Are there any other questions in the room? I don't think so. Thank you so much for your time, Anthony.
Yeah, thanks.